from Bio-Rad Laboratories. The title of our webinar today is Accurate and Reproducible Inline Dilution with Process Scale Chromatography Skids. My name is Herbert Engerer, and I'm the product manager for the process software. I'm pleased to welcome you here. And we have our expert here who is giving the presentation. His name is Sébastien Lefebvre. He is our sales support manager based in France. And he will give us some economic insight into chromatography with inline dilution compared to conventional chromatography. Also some information about precision. And we encourage you, if you have questions during the webinar, please use the box and chat with us. We are logging these questions, and after the webinar we'll have a question-answer time just to get back to you. If there will be not enough time for answering all your questions, we are very pleased to come back to you and answer by email. So let me hand over to Sébastien. Thank you.
Thank you very much, Herbert, and I'm very excited to be with all of you today. Well, before entering directly in the subject of inline dilution, I would like to step back a little bit about the general picture of process chromatography. Well, process chromatography is all about separation, and therefore to maintain resolution between the target molecules and all the other molecules, contaminants or other. So now, how does it translate in terms of hardware? Well, so it can translate in, depending if we speak about columns or process kits, in, let's say, different critical quality attributes. Concerning the columns, I placed here the formula which give the resolution related to the retention factors and number of plates. This formula is valid for isocratic mode, which is the most demanding, but it's also true for gradient chromatography. What it says is that it is very much linked to the interaction between the media and the molecules, and it is also very much linked to the numbers of plates. In other words, to the size of the beads and the quality of the distribution. But we're not going to speak about that today. What we are going to speak today is about process kits. And maintaining column resolutions for process kits can be translated into at least two very important critical quality attributes. The first one is to maintain a constant flow rate. The flow rate through the columns has to be stable. And the second one is to have a reproducible content and concentration of buffer. And this is all what it is about in inline dilution. So, concerning inline dilution, so why is it so important to have inline dilution for process chromatography skids? The first point is that it allows you to use very concentrated buffer, and therefore to reduce the size of the tank so as to save well the floor space into the clean room. It's number one. The number two is that for many chromatography purification, many methods, in fact, between the different steps, equilibration, wash, elution, regenerations, we're only using a few buffers, sometimes only one or two, but they are used with various concentration. Therefore, the inline dilution can allow you with one single tank to do all these different steps with different dilution ratio. And therefore, it is not only reducing the size of the tank, it is also to reduce the numbers of tanks, and therefore save even more floor space in the clean room. Also, for some process or some application, linear gradients are used. Well, usually at process chromatography, they have been translated into step gradients, but linear gradients are also possible. And lastly, during a process optimization, it is quite frequent to have to adjust very slightly the concentration of the buffers so as to optimize the purity or the yield. Therefore, these are all the main reasons for which inline dilution can be interesting. Something important to remind about inline dilution, especially when we dilute a concentrated buffer with water, is to not forget that this will have an influence on the pKa and on the pH. Here on this table, we take the example of sodium phosphate, and here we simulate a dilution of 0.5 molar sodium phosphate, which has been adjusted to pH 7. So when we get 100% of this concentrated buffer, we get a pH here 7, and the pKa is around 6.6. But as you dilute from 100% down to, for example, 10% of concentrated buffer, therefore 90% of water, well, you can see that the pKa is changing. And why it is changing? It is because you are lowering the ionic strength of your solution, and therefore the pH is increasing. And you can see that, well, it is quite significant because we have almost 0.27 unit pH, so it has to be taken into account. For example, if you want to make 0.05 molar NaO sodium phosphate buffer, starting with the 10x solutions, and you want to get it, for example, at 7.27, you know that you will have to start with a pH 7 with concentrated buffer. Just a reminder, because it's important to not forget it. Let's now spend some time about the economical interest of inline dilution, because before all, of course, it has some technical advantage that we have already seen, but it has also some very important economical interest. For this little study case, we have considered, well, two cases. The first one is a capture of human IgG with protein A, well, very classic, and the case two, capture of human IgM with CHT. And we have arbitrarily chosen a column, 60 by 60, and we combine it with a process kit size 3, which is our sizing, which go up to 1200 liters per hour, so which is a system suitable for this kind of columns. Okay? So if we consider the first case, so the IgG capture with protein A, well, typically for protein A, the chemical being used for equilibration and first wash, for elution, for regeneration are different. And there are a lot of applications like that where we don't use the same chemical. So it is not possible to have one single buffer which is diluted at various ratios so as to prepare these different chemicals. Therefore, well, if we consider this step volume, so 15 column volume for equilibration and first wash, 10 column volume for elution, and 5 column volume of regeneration, the only saving brought by inline dilution is, well, to use concentrated buffer. So here we took an example of 5x, so as to reduce the size of the tank. So we don't save numbers of tanks. We still have here 4 tanks. But so with the basic system, you see that the volume of this tank is quite important. So translated into size of tanks, we typically have tanks over 1 meter diameter. And so all of that would consume around 27 to 30 square meter in the clean room with the basic system without inline dilution. And also, as we have tanks, we have also to clean these tanks between each runs. And taking the general rules for cleaning of the tanks, which are given here, so these require around 8,000 liters of chemicals that can be acidic, alkali, water. Typically, it's a sequence. Okay. Now, if we go with the inline dilution, we can use much smaller tanks, and therefore we can save some space, some floor space, and we are also reducing the amount of chemicals for the cleaning. So now translated in terms of capitals, well, about investment, so the initial investment only. The process skids, of course, between a basic system without inline dilution and a system with inline dilution is, with inline dilution it has a cost, so you see here the difference. But you can see that there is some saving about the tanks. Here we take tanks with a scale because we have to scale the different buffers, agitated, with a clean in place, with pumps, and with a piece of software. And so you can see that, well, the fact that we reduce the size of the tank has some influence on the price. Same arises for the floor space. As if we consider the general rules of 2,700 euros per square meter for the initial investment of clean room, we have some savings. So here, already here with limited advantage with inline dilution, you can see that the inline dilution option is already paid back. And in addition, between each run, as we have reduced the size of the tank, we have also some savings. Here we consider 2 euros per liters as general for water, alkali, and acidic. So it's a general rule. It's very generic. Okay. Of course, this doesn't take into account the operating cost of the clean room. It's only speaking about initial investment and just savings about cleaning solutions. So it's very restrictive. If we take the second example, which is IgM capture with the CHT, it's another example. Well, you see here that between equilibration, second wash, elution, and regeneration, we are using the same buffer. So it's only a matter of inline dilution of the same buffer during these different steps. So not only we save, I would say, tanks volumes because we work with a concentrated buffer, but we can also reduce the numbers of tanks because here with the advanced system with inline dilution, we just need 2 tanks, one for the load and one for the concentrated buffer, assuming that the water used as diluent is coming from a water loop. So here you can see that the floor space saving is much more important because we have less tanks, and the same for the saving for the solvents or the chemicals used for the cleaning. So here, if we do the same calculations with the same rules, so you can see that about the initial investment, we save much more than in the first case. Because so you can see that the initial investment is almost 100,000 euros less. And in addition, we still have a lot of savings due to less cleaning, as we have less tanks and smaller tanks, and also as you have just to prepare 1 concentrated buffer tanks and not 3 or 4, you are also saving some labor for this preparation of concentrated buffers. So it is even more juicy. And again, here it's a very restrictive approach. We don't consider all the other operating costs that will have which will bring additional advantage. I forgot to mention that, of course, we have now more and more facilities running with single-use or disposable bags. In these cases, I would say the biggest saving is, of course, the floor space. Because, well, also about operating costs, because you have to replace these bags from run to run, and therefore you can use regular bags, not too big, and use it with inline dilution. So it is also very much interesting for disposable purification, downstream purification process. Now, inline dilution technically is quite a challenge. The first challenge is that we have some constraints linked to the instruments and the pump used. For the pumps, they have a limited flow range, and we have to accommodate with it. With the best, I would say the most, let's say, the best pumps which are sanitary in this market, we have typically a range of 25 if we make the ratio between maximum flow divided by minimum flow. So the maximum flow is 25 more than the minimum flow, so it's quite limited. And also, as what we said earlier, we want to obtain a reproducible resolution, and this to obtain reproducible resolution, we need to have a very stable and reproducible buffer concentration. And therefore, we need very high precision in terms of dilution. And for that, so we need to have very accurate instruments for controlling the dilution. Another challenge is that we want to minimize the transition time when we change from one step to the other, where the flow rate can change or the dilution ratio can change. And during this transition time, in some application, it is possible to bypass the column, so to stop the circulation through the columns. But in many applications, it is better to never stop the circulation through the columns. Therefore, what we want to avoid is to have overshoot. Overshoot is what you see here in red. You make a step gradient, for example, here, and you want to obtain this target value. And if your inline dilution control is overshooting, you are going to have this red curve, so you go above the target value, and then you stabilize over time. Suppose that you are doing here an equilibration, so and now you are injecting more salt than necessary, so you could here initiate elution, so which is not good. This is why it is very important to tune this inline dilution control with a green curve that you see here, so to have a smooth and fast transition to the new target value, but not exceed the value which is expected. So now let's go with typical installation that we can find for inline dilution. The conventional approach, the conventional skids look like a little bit this PID. Of course, from vendor to vendor, it can vary a little bit, but overall, typically we find two pumps. One would be especially for the dilutant, so water especially, and for the product. And this other pump would be for concentrated buffer. Okay, it can be eventually smaller than this one, so as to do high dilution ratio. We have then a mixing valve, we have a static mixer, we have a bubble trap that can be bypassed through the valves. Then we have the very famous column block where you can go downflow, upflow, or bypass, and then you have the instrumentation after the column, and then you have at least of course, two outlets, one for the waste and one for the good fraction. It's the real minimum. With conventional skid design, the inline dilution is typically controlled by flow, so for the total flow. The flowmeter can be after the column or before the column, it doesn't matter. For that, typically what is used is closed loop control. So for example, we have the pump are running at some speed, so we measure here the flow. If we find that the flow is too small, it is going to speed up the speed of the pump, and we'll have here some proportional integrate derivative parameters so as to do a good tuning of this correction. Same arise for the inline dilution, but this time the dilution is converted into conductivity, and therefore, so here if we inject too low salt, so not enough conductivity, this closed loop control is going to speed up the concentrated buffer pumps, and the opposite. Okay, so this is a typical situation that we can find. And therefore, what are the pros and cons of such solution? Well, about the advantages, this solution works especially for the purifications which are driven by ionic strength and which are defined by ionic strength. So in these cases, customers usually don't say, I want to have a 1.5 molar NS here. They say, I want to have 123 millisiemens per centimeters, because it is the ionic strength I need for my ion exchange chromatography. In this case, yes, it works, because conductivity is a direct measurement of ionic strength. And also the other advantage is that even if your concentrated solution, so what you plug to, connect to these inlets, is not precisely defined, as the system is going to self-tune to the target conductivity, it is going to obtain the right conductivity. Now, and also yet another advantage is that you only need to have one flowmeter. So you can, these instruments are quite expensive, so it minimizes the number of instruments. Now about the disadvantage, fact is that most of the purification, most of the applications are defined, the buffers are defined by concentration. So, for example, what we see with the two cases we have studied, for example, we want to have an elution with 100 millimolar phosphate, sodium phosphate. Okay? In this case, conductivity, the problem with conductivity for controlling inline dilution is that conductivity is an indirect measurement of concentration. We are not measuring concentration, we are just measuring the ionic strength. And this relation between conductivity and concentration differs between each kind of chemicals. And it's quite hard to predict for mixing. For example, mixing with low acidic, with low alkali, so as to make a buffer. Okay, and also if you are using buffers which have a very low conductivity, such as MES, FS, which are very much used for ion exchange chromatography, well, using conductivity control is not very much suitable. I here show in this graph, I would say the relation between the conductivity and the concentration for several kind of buffers. So, for example, sodium acetate, ammonium sulfate, potassium phosphate potassium, and NaCl. And you can see that, well, first, it is not linear. It's something quite known. And you can see that depending on the chemical, the law is quite different. This slide also shows something else which is very interesting. It is the consequence of not measuring directly the concentration. If you work in volumetric, I mean you want to have a concentration with your buffer, you have to take into account this very much this point. With conductivity probe, the typical error of such instruments is plus or minus 2% full scale. It's already a good performance, and it is what is usually obtained with conductivity probes. Suppose that your full scale is 300 millisiemens per centimeter. Therefore, your error will be plus or minus 6 millisiemens around your target value. So now suppose that you want to make inline dilution and you want to prepare 1.5 molar NaCl, so which correspond to 126 millisiemens. So due to your error, in fact, actually you are going to navigate between 120 millisiemens to 132 millisiemens. So it is plus or minus 6 millisiemens. And when you translate that into concentration, you see that you are going to navigate between plus or minus 5.6%. So in other words, this plus or minus 2% of error is now translated as plus or minus 5.6%. So, and in addition, you probably know that conductivity probe is very much, the conductivity is very much sensitive to the pH and also to the temperature. So this is why with the conductivity measurement, there is a temperature compensation. And us, we use typically KCl for making a general temperature compensation. And you are not using KCl, you are using something else. This is going to bring an additional error, typically 0.1% for each degree Celsius around 25 degrees. So at the end, in fact, you try to control an inline dilution with an instrument which has at least a 5.6% error. So this is why our conclusion is, okay, inline dilution controlled by conductivity is good if you directly work with ionic strength, but it is really not the optimal solution if you want to work in volumetric, i.e. to obtain a target conductivity. Okay, that's it for the disadvantage. And also, as we have seen, the measurement error, which is quite significant. Okay, at Bio-Rad, we have taken another approach, which is, okay, conductivity is good for controlling, especially or making inline dilution if it is controlled by ionic strength. But for volumetric dilution, we prefer to use two flowmeters, very high accurate flowmeter, the top in class. We have the same configuration, but here instead of controlling the dilution with the conductivity probe, we prefer to use a flowmeter. So this flowmeter will control, I would say, the inline dilution, while this other one will control the total flow of the skid. So what it makes into in difference? The first one is that as we use two flowmeters, we are directly working on volumetric. So this is really the best solution if the buffers are defined by concentration. So if your application is defined by concentration, we have a direct measurement. Also, one other advantage is that the flowmeters, which can be massic or electromagnetic, they are much more precise than the conductivity probe. Typically, the measurement error is less than 0.5% error. And if you are using the optimal of the range of the flowmeters, it is going to be plus or minus 0.15 to 0.20% of error. So which is almost 10 times less than the conductivity probe. Another advantage is that the dilution is not sensitive to the kind of chemicals. It can be saline buffer, which have a high conductivity, or zwitterionic buffers, such as EPS or glycine, which have a low conductivity. As we know that the most important instruments in the skid are typically the flowmeters, because they drive the flow, they drive the buffer concentration, we are going to optimize the choice of flowmeters for each customer project, so as to use the best in class and the most adapted to the flow range and the dilution range. Okay? About the disadvantage, well, of course, it costs an additional flowmeter compared to the first solution, but it is widely justified. If the buffers are defined with ionic strength, we can still control, if necessary, the dilution by conductivity. But if the buffers are defined by concentration, conductivity probe will be still used for detecting significant deviation. For example, making warning or pausing alarms if we are running out of lines. And what could explain that is that the mother solution is not conform to what is expected, because the skid is just going to make inline dilution. It is not going to change the dilution ratio unless you ask for conductivity compensation, which is a possibility. And so the critical point is to prepare a precise mother solution. But it's normal practice in pharmaceutical industry, so there is no real concern with this. So now, well, there were a lot of explanation about theory. Now let's go to practice, so as to show this performance of such solution. For this performance evaluation, in fact, we have used here the skid size 0, which is capable to go up to 120 liters per hour. So we have used several flow rates, 40, 80, 120 liters per hour. We have used several different dilution ratio from 10% to 90% of concentrated buffer. For evaluating the performance, we have used the UV absorbance for evaluation. Why have we used UV absorbance? The first one is that UV has very good proportionality of signal versus concentration, and also a very good sensitivity, much better than the conductivity. So this is why, in order to really finally evaluate the performance, it's better here to use the UV, just for qualifying this inline dilution. So therefore, as we use UV absorbance, we have used something which absorbed in UV, so we have used caffeine solution. So we have made an inline dilution of high caffeine solution with 57 milligrams per liter, with a low caffeine solution at 5.7 milligrams per liter. And we have measured the absorbance at 272 nanometers, which is the optimal for caffeine. So now what have we evaluated? The first one, so I prefer to show this one, it is how much time it takes to obtain the right dilution. Then it is also to see how precise is the inline dilution. For that, we have prepared offline dilution, volumetric dilutions, so using graduated vessels, so as to draw a reference curve, and we have tried to reproduce the same dilution with process kits, so as to see if there is a difference. And we have measured how stable we are once we obtain the right value. And for measuring how stable we are, we use capability, which is quite very much used as a quality, let's say, attribute. It makes a ratio between the tolerance interval and the standard deviation. In fact, it is very much linked to the Six Sigma quality objective. So when we have a capability over 1.33, it means that 99.99% of the points are within the tolerance interval. So we are more like that than like this. So well, you see here the offline dilution, so volumetric dilution performed with graduated vessels. So you can see, by the way, that effectively UV is very much linear with the concentration. And this allowed us to obtain what should be the target absorbance when we perform inline dilution. And then we reproduce the same dilution with a skid. So you can see here at 40 liters per hour with a different dilution ratio. So you can see, by the way, that there is no overshoot. You have in pink here the total flow. You have the concentrated buffer flow in orange here. You have the UV absorbance in purple here. And you have the dilution factors showed here. Okay. Then the same at 80 liters per hour. Again, we see that the total flow is stable. And we see that also the dilution are stable. And lastly, at 120 liters per hour. So as a conclusion, you have here what we obtain with different flow rates, with different dilution. So here in this column, you can see what were the absorbance expected. So what is what absorbance is expected based on the reference made with offline dilution. And you can see here what we obtained with the skid. And you can see that the difference here is very minor. In fact, it is just the resolution of the signal, plus or minus 0.01 DO. So we are very accurate with inline dilution. You can see here how much time it takes to open the target value. And you can see that the transition time is around 30 seconds. 30 seconds, I would say we have to remind that we don't want to have overshoot. So we have to be, let's say, fast, but we have to be quite conservative so as to not stress too much the inline dilution and have overshoot. But 30 seconds is quite good results. And you can see here how much we deviate around the mean value. So always less than plus or minus 2%. But if we speak in terms of capability, so what is the commitment of Bio-Rad to obtain 99.99% of the points within the tolerance? And you see that in the extreme, let's say, dilution ratio, we would be at plus or minus 3%, and in all the other cases, we are at 2%. But what you see here, it is not only to say we are not going to have error plus or minus 2%, it is really a commitment linked to quality attributes such as the capability. So if we now conclude all of this presentation with the take-home messages, the first take-home message is that if we work with volumetric, so if the buffers are defined with concentration, it is much better to have inline dilution control with flowmeters because they have much more precision and because they are directly measuring what is expected, so the volumetric. With the conventional approach, with the conductivity probes, we have more error, at least 2% full scale, so at least 4 times, if not 10 times, because measurement error with flowmeters can be much lower than that. And so what matters is to work in volumetric and not to work with indirect measurements such as conductivity. And now the last take-up message is that flowmeters are paramount, and this is why in each case we are consulted. We are doing a worst-case analysis where we consider your process description. We take the worst-case dilution ratio. For example, we work at small flow with a high dilution ratio. And here we optimize the choice of the flowmeters for obtaining the minimum dilution error. Okay, so as to have the most suitable choice in each cases. Thank you for your kind attention.